In the 19th century, all tyres were still made of solid rubber. John Dunlop's invention in 1888 changed this. Using a fabric-covered rubber tube, the pneumatic tyre was born, and with it, a cushioned ride. Later, tyres were made of rubber with a vulcanized fabric layer inside. This made them much less susceptible to punctures. The cars were also getting ever faster. New wheel shapes and rubber compounds made the tube obsolete. Air tightness was achieved by covering inside the tyre. The 50s saw the rise of the cross-ply tyre. This modern concept with diagonal layers of nylon or steel threads made the tyre more durable and better for high speeds. These tyres, however, were not very firm and could distort badly when cornering. This was corrected in the 1970s by the radial tyre. The diagonal layers were redesigned and complemented by a lengthways belt of steel. This division of labour gave the tyre not only stability but also made it more resistant to extreme temperatures and permitted new styles of tread. Today's high-speed tyres use the same principle but are made of high-strength synthetic fibres and modern rubber compounds, thus allowing constant speeds of 300 kilometres and more. Be it DTM, endurance or cup races, every series has to cope with the whims of the weather. A slick tyre without any tread stands little chance in the wet. Its contact with the surface is soon lost, as from speeds as low as 60 kilometers an hour, a cushion of water forms beneath it, lifting the tyre clear off the track. In the worst-case scenario, this aquaplaning makes the car impossible to steer. So the water has to go. Meet the dedicated wet weather tyre. The special channels in its tread are designed to funnel the water away and push it out to the side. This delays any cushion of water forming and keeps the tyre in contact with the surface. To maintain the maximum amount of rubber on the track, the trick is to make the channels as narrow and efficient as possible. A direct comparison clearly shows that wets make sense whenever there's water on the track. They allow much higher speeds and hold the line in corners long after slicks have aquaplaned away.
In no other motorsport is the importance of tyres so apparent as with motorbikes. They bring over 200 horsepower to bear in tough infights, and that on a contact area the size of a small coin. In turns, nearly the entire width of the tyre is used, and the contact area changes constantly. Different rubber mixtures are used for the center, shoulders and flank areas to provide optimum performance in all positions. The tyre can barely deform at all. It always transfers forces longitudinally and laterally and is an elementary component of safety. In the rear, 4 plies of synthetic fibers provide extreme stability. Modern technology lets the tyre take and transfer power optimally, even at low air pressure. The front tyres have a smaller design. Because they don't convey traction, the focus is on steering precision, low weight and braking stability. The constantly changing angles and loads in motorcycle racing tyres demand a special design for constant grip and predictability in all situations.
Hidden beneath the low, broad silhouette of a racing car lies highly complex chassis suspension technology. It's this that makes it possible at all to keep the tyres on the ground under extreme race conditions. To make the tyres contact patch straight, the upper and lower wishbones are the same length, which however is not always advantageous. If the upper arm shortens, the tyres tilt inwards when the spring compresses, creating a negative camber. This stabilizes the car in extreme situations. Although race circuits may seem very flat, they're not. The suspension constantly has to delicately maintain and cushion contact with the track. With hard springs, here red, the wheel only gives a little. The tyres get pressed down hard and maintain long ground contact. However, going over major bumps, they can also lose this completely, so hard springs are ideal only on flat surfaces. Therefore, matched to the circuit, softer springs, here in yellow, also get used. In direct comparison, it becomes clear that a softer suspension maintains smooth contact with the ground for longer. Handling on very uneven surfaces becomes more predictable, and the car is steadier. Getting the chassis suspension right can make the difference between victory and defeat. For fast lap times, every driver needs a car that handles predictably. He's got to know what will happen when he turns the wheel. It sounds simple, but it's not. The interplay of suspension and tires with the car's steering is much greater than the turn of a steering wheel might suggest. The reason for this is the hugely different forces exerted on the car as it moves. As the car goes into a corner, centrifugal forces push outward, and it actually wants to carry straight on. Also contributing to this are the circular forces created by the rotation of the tires. The higher the speed, the greater the power needed to overcome them. What helps to stabilize a two-wheeler creates inertia here. What actually happens when you turn the wheel? The rotary momentum is transferred via the linkage into the steering gear and ends up at the tires. The forces produced in this process are transferred via the tires to chassis and suspension back into the car. Another element, the vertical forces, i.e. upward shocks. Whenever shocks are absorbed, they get into the car body and unsettle it. The complex effects of all these forces added together have to be dealt with by the exact interplay of steering system, chassis and tires, so the car handles predictably in all circumstances. Motorsport puts a huge strain not only on car and driver. Extreme loading, wear, grip. The demands on the tires are enormous too. The secret lies in their makeup. The bead spans the wheel rim and provides a firm hold. Running up from it, the radial plies get continuously laid in multiple layers, creating the foundation for stable handling. The lengthwise layers, or bias plies, are made of high-tech materials such as Kevlar. They conduct away heat, are lightweight, and make the tire fit for high speed. Every ply is precisely tailored to the tire's intended purpose, as is the compound, which is unique to each type of tire. The carcass, consisting of plies and bead, has the compound poured around it in a mold and then gets heated up at around 250 degrees. This produces a very firm and yet elastic combination, the race tire. The finished tire is a high-tech product designed to deliver outstanding performance. It's made of a broad mix of ultra-modern materials, with new components being constantly tried. Each race series faces the same challenge when it comes to tire pressure. If it's correct, the tire lasts well, heats up properly and provides a stable ride. However, less pressure also means a greater contact area and thus more grip. But if the pressure is too low, the tire begins to deform, with this deformation going deep into the tire, causing it to get too hot. This makes it less durable and can even lead to blowouts. The tire also becomes unstable in corners, steering precision suffers, and it gets hotter still. Only at the right pressure do tires remain durable and easy to steer. Firm tire walls are also incorporated into their design. Modern tires can sustain constant speeds of close to 300 km per hour, but can do nothing at all without the correct amount of air. Regardless of the race series, for a racing driver, tire durability during a race is a decisive factor. People often talk about right or wrong tires, yet every race tire is a performance artist and put under extreme strain. The interplay between tread, tire shoulder and tire wall begins with the bead. It holds the tire securely on the wheel rim. A large contact patch delivers great force onto the ground. If you also reduce the air pressure, the tread gets a lot hotter and durability goes down. Firm tire walls reduce this problem and increase cornering stability. The tire also has to protect the wheel rim. It mustn't get damaged even by major bumps. The demands made of tires are high. Optimum tire performance allows driver and car to always maintain their place in the toughest of races, even under extreme conditions. Why is lightweight construction so important in racing? In addition to the relationship between engine power and vehicle weight, there's also another hidden reason: unsprung mass. Whenever a car goes over a curb, the tire gets pushed up. When the impetus has waned, its weight and that of the car pushes it back down. For optimum performance, a wheel should lose contact with the ground as little as possible. It's now the job of the springs and shock absorbers to press the wheel as evenly as possible onto the track and to quickly dampen any vibrations. The better the suspension is set up, the more track content the tire has over bumps. Everything that has to be dampened by the springs and shock absorbers is called unsprung mass. So that's a part of the suspension, brakes and wheel. It's the furthest away from the springs and thus has a greater leverage effect. If it's heavy, as in this assembly, then a lot of force goes into a lot of mass and takes a long time to dampen the vibration. If the weight is now reduced in wheel and tire design, the same amount of dampening can reduce vibrations much more quickly. Less unsprung mass thus allows a more precise chassis setup and thus a better track surface position going over bumps. As a racing car speeds along, transverse and longitudinal forces cause its tires to heat up. Indeed, it's a required effect, as at the optimum temperature of around 90 degrees, the tire surface is so soft that it positively interlocks with the asphalt. But if the track surface is too smooth and doesn't have enough grip, wheels skid when cornering, and the tread heats up more than the rest of the tire. That causes graining, small particles of rubber forming on the running surface of the tire. Whenever a tire skids, the extremely sticky layer flakes away from the remaining cooler part and gets stuck as rubber grains on the tire's hot surface. All these little particles soon form a loose layer. The car starts to skid on this layer as it corners. Treaded tires, especially wets on a dry track, suffer a similar fate. If the lateral forces in corners are too great, then as the tire skids, the edges of the tread blocks heat up and wear away badly. They quickly become rounded and both steering precision and grip suffer. In the case of racing tires, the deterioration on dry surfaces is even faster. Close observation shows that a smooth, fluent driving style reduces graining. Over the full race distance, that can be the decisive factor that clinches a win.